which makes a lot of sense in the era of LSST. Prolifically involved, should we say.
Yeah, we had some ideas here. I mean, Rodrigo actually had a proposal of having a whole array of 50 small telescopes.
Yes, that's right.
Listed north, south in Brazil, but we didn't get the money yet.
Yeah, money. These days, money.
It's always a problem, isn't it?
It's always about money. Do you know David Buckley?
Yeah, I know him.
Yeah. So
I mean, I know who he is. I don't think we ever spoke to each other.
Yeah, so he's also one of the LSST PIs, and he and I, we don't directly collaborate a lot, but we're sort of quite well aware of each other's efforts. So he's very into this idea of having these small telescopes all around the world for.
Yeah, but besides the small telescopes, there's the idea of data processing, right? Which is something that interests us a lot. And that would be nice to actually have some exchange. Anyway, I actually I listened to one of your talks, I think in ADAS. That's why you were invited. I really was really a very nice talk.
This will be quite similar.
Well, it doesn't matter. I'll listen twice.
Oh, thank you very much, Luis. It's nice to meet you.
Okay. Anyway, I think it's time to start. Okay, we'll talk later.
Thank you.
Okay, thanks, Luis. Well, let's start. I'm going to do a short introduction, and then I will pass you the floor, okay? Let's just record it. All right. Hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or on our YouTube channel, LIneA MCTI. This is our first webinar of the year, and to help us to do so, we have the pleasure of having Dr. Michelle Lochner, Senior Lecturer at the Department of Physics and Astronomy of the University of the Western Cape. Her research focuses on rethinking how to do scientific analysis in the era of massive datasets, which largely involves developing new machine learning and statistical tools to best leverage new astronomical data. Dr. Lochner is also heavily involved in the efforts to optimize LSST's observing strategy. So without further ado, and hoping those brief words have done at least a little justice to all your hard work, I'd like now to handle the floor. So Michelle, thank you very much for being with us today. The floor is yours.
Thanks very much, Rodrigo. It's really great to be here. So I'm just going to share my screen. Great. So thank you all for coming. It's really wonderful to be here and give this talk. I'm very excited about quite a lot of things happening in astronomy at the moment, mostly all this wonderful big data coming in, which motivates using things like machine learning to make scientific discoveries. So that's what I'm going to be talking to you about today. I'm going to have a little bit of an introduction to machine learning for those who aren't very familiar with it, but I'm mostly going to be talking about anomaly detection. So to kind of set the stage, I want to start with the two projects that I'm the most excited about at the moment and the most heavily involved in. The first is the Vera Rubin Observatory, which is an optical telescope under construction in Chile. Some of you might remember this being called LSST. It's been renamed, and the LSST part now refers to the big 10-year legacy survey of space and time that the Rubin Observatory is going to undertake. And this telescope is very special because it's very big, but it's also very fast. So it's got this wonderful large field of view. It can observe very deep, and it can also do this very quickly. So it's going to make like a movie of almost the entire southern sky. And here's just an example of what kind of things we might expect from this telescope. Each one of these dots is a simulated supernova discovery. And a good thing to keep in mind is the dark energy discovery of a few decades ago was made with about 40 supernovae. And we're talking about 500,000 really well-measured type 1a supernovae by the end of this survey. So it's pretty revolutionary for quite a lot of fields, such as cosmology. And the great thing to keep in mind, one number to keep in mind as I give this talk, is not just the number of supernovae that we're going to expect, but just the number of transients in general. So every single night, the Rubin Observatory will detect something changing on the sky about 10 to 15 million times a night. So 10 million times a night, it's going to issue an alert. And maybe half of those will be false positives. Probably a lot of them will be satellites, cosmic rays, things like that. But that's about 5 million real astrophysical objects changing in brightness every single night. So it's an enormous data set, and there's a wonderful potential to discover something new and interesting, but how do we sift through such an incredible amount of data? On the other side of the spectrum, the other telescope that I'm very excited about is the Square Kilometer Array. So this will be the biggest telescope ever built. It's a radio telescope under construction, part in South Africa, that's the mid-frequency array, and partly in Australia, which is the low-frequency array. And the data rates coming from the SKA, the expected data rates, are just enormous. You know, easily the internet traffic every day, petabytes of data. It's an incredible data processing problem to try to handle this amount of data. But even the processed data, even once you've done all the effort of getting images out, we're talking about catalogs of 1 billion galaxies easily, hundreds of thousands of radio transients, many, many more fast radio transients. So it's also an incredible data challenge to think of how to make discoveries with this enormous instrument. And although the SKA construction has just started on the SKA, which is really exciting, but we're already in this era of data deluge in radio astronomy. We have a number of what are called precursor telescopes. So one is, or Pathfinder telescopes. One is MeerKAT in South Africa. That's an absolutely beautiful instrument. I'll show you some gorgeous data a little bit later. But you know, this is a field where astronomers are used to being able to download data to their laptop and do the analysis there, and it's already impossible with MeerKAT. You know, a single observation could be a terabyte easily. And even worse is ASCAP in Australia, which is a beautifully designed survey telescope. So they've done some amazing surveys already of almost the entire southern sky. And it's just an enormous data set, and we're really not used to even working with this kind of scale data. And then, of course, there's LOFAR in Europe, which is doing very similar things in the low frequency radio spectrum. So these telescopes are already revolutionizing radio astronomy. It feels like just about every week a new discovery comes out. So it's a very, very exciting time, but the data challenges are quite severe that we have to deal with. So basically, we're facing a data explosion. I feel like this picture encapsulates the emotion when it comes to all this wonderful, beautiful data, but it's really an enormous amount to deal with. So a very obvious set of tools to look into to be able to solve problems, you know, problems that we used to do manually, we want to now solve automatically, and we can do this to a large extent with machine learning. So I didn't want to assume that everybody is necessarily a machine learning expert. So I want to talk a little bit about what is machine learning. So the first example I want to give, which is really, if you read machine learning papers, 95% of them are going to fall into this category, which is supervised machine learning. So the idea is that you have a data set, and you are, say, for instance, trying to classify these objects into whether it's a circle or whether it's a cross. So you want to create an algorithm that's going to be able to automatically tell you, for a new object, does it belong to the crosses or the circles? So if I was to put supervised machine learning into one sentence, I would say it's a way to automatically learn a model that maps inputs to outputs, and it requires a training set. So the idea is, even in this case, which is really simple, you as a scientist can come up with a very trivial linear model to say, oh, anything on this side of the line is a circle, anything on this side is a cross. But in practice, with the kind of problems that we try to solve, they are so complex that we have no possible way of coming up with a sensible model ourselves. And so the machine learning algorithms are ways to automatically generate that model in a completely data-driven way. Just to try to demystify the field a little bit, this is an example of a neural network. So neural networks are arguably the oldest machine learning algorithms, certainly the most popular at the moment. And the reason I want to show you this is actually something I give to my students when I'm teaching machine learning. And this is an example of the simplest neural network that I could think of, where you have some input data that comes here, you have a hidden layer of neurons here, and you have some output that you're trying to predict. So in the case of the previous example, the input data might be the coordinate of this point on this plot, and the output would be the class that it belongs to. And so given a new set of coordinates, you'll want your model to be able to predict the class that it belongs to. And the nice thing is that for this network, the exercise I give my students is to actually write down the equation for the output in terms of the inputs and the hidden neuron weights. And I do this to demonstrate that even though these models are very complex, in the case of deep learning, they can contain millions of parameters. At the end of the day, it is still just a model. And all we are doing is a kind of very complicated modeling. All right. So just some definitions. I just want to breeze through this so I can spend a bit more time on the anomaly detection, but I just want to point out a couple of things with this flow diagram. The first thing is that whenever we talk about machine learning, we always start with data. Machine learning is a data-driven field. Whatever you do, you're starting with data. Unlike in, you don't necessarily start with some hypothesis that you want to test, you really start with data. And then you have some problem you're trying to solve. A key thing to bear in mind is that usually you can't throw raw data at machine learning algorithms. You need to do some kind of feature extraction. So feature extraction is basically a way of simplifying the data. So it could, for instance, reduce the dimensionality. If you think of an image, for instance, that's actually a very high dimensional data point. There could be thousands of pixels. So you might want to do some kind of feature extraction to simplify the data down. But it's not just about dimensionality reduction. It's also about almost translating the data into something that makes it easy for the machine learning algorithm to solve the problem that you want to solve. And I should point out that if you've heard of deep learning, which I'll talk about right at the very end, the allure of deep learning, the reason why it's so powerful is it kind of lets you skip the step of feature extraction, or rather it has an automated way of doing the feature extraction, which is traditionally the hardest part of machine learning. And then you branch off into two different areas of machine learning. The first area is the one I've just been talking about, which is supervised learning. So that's where you have some subset of data for which you know the answer, and you want to train an algorithm to be able to predict it. So that data can be obtained in many ways. Often it's just literally a human being sitting there looking at a bunch of images or light curves or spectra and manually labeling them. And then once you've got enough, you can do your machine learning. Or it can be obtained in different ways. And like I said, pretty much in the field of machine learning, 95% of papers fall into this category. That's really where most of the focus up until now has been. And you can split it into two different types of problems that you want to solve. The one is if you have categorical data, like the example I just showed with the circles and the crosses, or if you had pictures and you were trying to identify cats and dogs or whatever, then it would be a classification problem. Or if you're trying to predict something continuous, like the redshift, for instance, or the amount of rainfall the next day, that would be a regression problem. In practice, these two problems are solved in very similar ways. So this all just lumps into supervised learning. What I'm going to mostly talk about in this talk is actually unsupervised learning, which is what to do in the situation where you have no labels at all, right? So you've just got some data coming in and you've got no labels. You don't know what you're looking at. You're not trying to solve any specific classification or regression problem. And I think this is really important because we often find, especially with telescopes like MeerKAT, we keep finding things that we haven't really seen before because of the sensitivity of the instrument. And we're now in this regime where we actually just don't have training data for these types of objects, but we also have a lot of data. So this is the regime where unsupervised learning becomes very powerful. And in this talk, I'm mostly going to be talking about the anomaly detection branch. Before I go into unsupervised learning, I wanted to just give a real example of supervised learning that I've been working on for many years, which is supernova classification. So remember I showed you that video of all the supernovae going off many times a night. That's going to be an incredible data set, and we're especially excited to do cosmology with it. But the problem is there are different types of supernovae. So there's the type 1As that are very useful for cosmology. They can be used as distance indicators. And then there's kind of everything else, that if you're a cosmologist, you don't care about what goes in the everything else category. If you are an astrophysicist studying supernovae, I think you do care quite a lot about what goes in this category. But the point is, if you want to do any kind of real science with supernovae, you have to know which class they belong to. The trouble is, with Rubin detecting 10 million alerts a night, it is a photometric only instrument. So that means it basically just takes a picture of the sky. And it takes a picture in different filters, but there's only 6 filters, right? So we don't get any spectral information from this telescope. And that's tough because the spectrum is by far the most reliable way, and it's up until relatively recently been the only way to classify a supernova. So we're kind of stuck. You know, we have this amazing instrument, this enormous data set, but we can't classify these objects. And we can do follow-up using other telescopes, but it's very expensive, and we'll only be able to spectroscopically follow up a small fraction of the Rubin data set. So what do we do? So a few years ago, so back in 2016, I worked on trying to solve this problem with machine learning. So the idea is that you have something that looks like this. This is a supernova light curve. So brightness is a function of time. And these are in some of those different filters that I mentioned. This is a simulated supernova from the Dark Energy Survey. And the goal is, given these light curves of different supernovae, you want to try to classify them into different classes. In this case, with the simulated data, we had just 3 different classes. In reality, there's quite a few more supernova classes. And so we were able to build a machine learning framework that was able to fairly accurately, I mean, not 100% accuracy, no machine learning algorithm is 100% accurate in general, but reasonably well classify different types of supernovae, and we published this paper on it. Something that I wanted to highlight, though, is for those of you who maybe are excited about machine learning, getting into the field, is an example of where the real challenges can lie in this field. So this paper was written with a set of simulations that were fairly simple. They simulated the Dark Energy Survey, which was really focused on supernovae, this part of the survey. So it had a very regular cadence. The data was very nice. The models were very simple in the simulation, and so the algorithm we came up with worked really well. Fast forward a few years, and there was this cool thing called the Plastic Challenge, which was a public challenge to try to classify all types of transients from a simulated LSST dataset. So it was much more realistic. It had much more realistic models and very difficult data, lots of missing data, lots of gaps. And when we used the same approach, it just didn't work. We have very poor classification performance. And we had to work for many years. This is work led by Caterina Alves. She's a PhD student at UCL. And she worked very hard for a couple of years, actually, to be able to update the algorithms to deal with the plastic data. And most of the work, very little work had to go in the machine learning or even the feature extraction part. Most of the work had to go into managing the data. The data had to be augmented in the right kind of way and processed in the right kind of way in order to be prepared for the machine learning algorithms. And it really took a lot of truly understanding the data and understanding the limitations to be able to develop this framework. And this has really been my experience, that the machine learning part is usually very easy. It's dealing with the data and the pre-processing and dealing with the feature extraction. That's actually the hard part. And these algorithms can be very sensitive to how you actually process the data. So that's just an important thing to keep in mind if you're interested in this field. Okay, but enough about supervised learning. I promised you anomaly detection. So let's talk about that. So I think everybody has an intuitive sense of what is an anomaly. It's really anything rare, okay? Anything that's different from the norm, anything that's weird. And we know about a lot of types of anomalies in astronomy, and I call them known unknowns. So, for example, gravitational wave events, particularly binary neutron star mergers, are pretty rare, but we know that they happen. Strong lenses are quite rare, and the fast radio bursts are relatively rare. So these are events or objects that are still very rare, so they do still constitute anomalies, and because they're rare, it can be difficult to build training sets to design classifiers to go look for them, but we know about them. Of course, the most exciting anomalies are the unknown unknowns, the new anomalies, the things that we weren't expecting, the truly new scientific discoveries. And my favorite example of this is the 1967 discovery of the pulsar. And I like to give this example because, I mean, pulsars completely revolutionized the field. Nobel Prize later, not awarded to the discoverer, by the way. Hugely important impact on the field. And yet, what did it take to make this important discovery? It took a very bright grad student carefully looking through her data and noticing something weird. And if she hadn't noticed it, I mean, probably eventually they would have been discovered, but it really took this smart human being laboriously checking her data to make this discovery. So the question that I have is, how are we going to make these kinds of new discoveries when there's 10 million alerts a night? When your data set is 1 billion galaxies, when the data is just so big that there aren't enough grad students in the world to look over it and find the interesting things. So this is the research question that's been preoccupying me for a little while. So if we think about how to use machine learning for anomaly detection, because you can, the way these algorithms tend to work, they're fully unsupervised, so there's no training involved. There's no training data. There's no labeled data. By definition, we're looking for something that we've never seen before. We can't have any labels. So these machine learning algorithms tend to try to learn kind of what normal looks like, and then anything that appears far away from the norm, by some definition of far, will tend to have a higher anomaly score. So in this way, you can automate the search for anomalies in large data sets. So just to give I'm not going to go into details, but a couple of brief examples of anomaly detection algorithms, if you want to look them up yourself. The one is isolation forest, which is built on the very popular random forest machine learning algorithm, where the idea is that it tries to isolate each individual point by making a series of cuts. And the idea is that a point that's weird, like this one, only requires a few cuts to separate it out from the rest. So it's probably more anomalous than one that requires lots of cuts. And similarly, there's the local outlier factor algorithm, which essentially is just a density-based algorithm. So it just looks for points in low density regions. Other anomaly detection algorithms that I've worked on with collaborators include BADAC, which is the Bayesian Anomaly Detection and Classification. I'm very fond of this algorithm because it's a statistical approach. It's a statistical machine learning algorithm. And it's designed to incorporate uncertainty, which is not something that happens with most machine learning algorithms. You have to remember, the development of machine learning has been largely driven by industry. And if you're Google and you're trying to build the best image recognition algorithm in the world, you probably don't care about the uncertainty and the precision on your parameters, whereas we as scientists really do care. So very few machine learning algorithms can naturally incorporate uncertainty information, and that was why we built BADAC, which is able to do it. And then another algorithm that I was peripherally involved in is DRAMA, which is really a framework. It's a whole framework of using deep learning algorithms to find representations of your data to be able to do anomaly detection. But when my collaborator, Bruce Bassett, and I were initially starting to work on this problem, we realized pretty early on that anomaly detection alone actually isn't enough, especially when you're faced with 10 million alerts every night. And that's because even if something is anomalous, it doesn't mean it's interesting. So in the example here, I've got a few artifacts from some image data, and I've got a few real sources. And I might not be interested in these at all, but I'm interested in these. But what we realized is that what's interesting is actually quite subjective. So what's interesting to one person might not be interesting to another. If I'm interested in data quality and I want to know about the artifacts, these might be the anomalies that I want to look at, whereas I'm not interested in these at all. Or even if I'm interested in real sources, I might be interested in different types of sources. And I can't tell you beforehand what it is that I want to find because I've never seen it before, right? So there's this inherent subjectiveness when thinking about anomaly detection that isn't really there when thinking about things like classification. So we wanted to build a framework that was sensitive to this type of subjectiveness. And we decided to bring in active learning. And I think active learning really plays a critical role in any practical use of machine learning in the real world. But in particular with anomaly detection. So the idea behind active learning is that you combine the raw processing power of your machine learning algorithm with the intuition and experience of a human. The goal is to make the best use of human expert time, because our time is very valuable, whereas a machine learning algorithm can process 10 million objects no problem. It's that's too much for me as a human. I can do maybe a few hundred. So you really want to make the best use of the time that the human has. You don't want them looking at random subsets of data. You want them only to look at things that are going to be useful. And so with this in mind, we built a framework called Astronomaly. So Astronomaly is a very general purpose anomaly detection, an active anomaly detection framework. So the idea is that it can take in almost any type of astronomical data, and I'll show you a few examples shortly. It can take images, time series data, spectra, more or less whatever you want. It can then do feature extraction, and this is really the most important and most difficult step, because the type of features you choose will dictate the types of anomalies you'll be sensitive to. And that's not great because, we want to guarantee we're going to find all the interesting anomalies in the universe. But unfortunately, that's impossible because something could be anomalous in any kind of weird way that my algorithm is just not designed to detect. So we have to try to use features that are general but sensible enough to be sensitive to the things that are at least physically possible and might be interesting. So there's a few feature extractors already built into Astronomaly that you could choose from. And then it runs anomaly detection. And again, there's a couple of different machine learning algorithms that you can choose from. Everything up to this point is pure Python, a fairly standard unsupervised machine learning pipeline. What's really important is this step, which is the active learning step. So after you've done your anomaly detection, Astronomaly will now display a user interface that I built on JavaScript, so it runs in your web browser, and allows you to interact with the data. So you can go through the data, and it's ranked from most anomalous to least anomalous, and then you can provide labels. And the labels are actually just how interesting is this object to you. And it then applies a novel active learning algorithm that we came up with that improves the aim is to improve the detection. So it doesn't actually change anything about the anomaly detection algorithm. It just basically reweights things. So it's a way of teaching it, at the very least, what you're not interested in. So if an anomaly crops up that you've never seen before, it's still going to show it to you. But if something appears that's similar to something that you said, I'm not interested in this, it's less likely to show it to you. It's going to prioritize things that either you haven't seen or that it knows you are interested in. The paper is out if you want to read it, and the code is publicly available. I'd love for people to play with it, run it on their data, and obviously I'm happy to help when you get stuck. But enough talking, let me show you what this actually looks like. So here's an example using Galaxy Zoo, which is a very famous citizen science project where average people took part in this great scientific endeavor of classifying different galaxies. And so it's a very large labeled data set of galaxies, and I thought this was a good one to try it out on. So this is just a random subset. So if you want to get a feel for what your data looks like kind of on average, you can just order it randomly and then go through it. You can see that most of these galaxies are fairly boring ellipticals or spiral galaxies. If you run the anomaly detection algorithm and order it from most of these anomalous, you see it does a pretty good job picking out things that are pretty unusual. There's things like tidal streams, there's interacting galaxies, but if you watch, there's also a few artifacts and things we're probably not interested in. And so if you look at the bottom, the buttons are changing color. So that's me labeling the data. And you only really have to label a few, maybe 50 or so, which takes a minute or less. And then you can actually run the second layer of machine learning. And if you order it from using the active learning score, you can see that it's kind of down-weighted the things that are more artifact looking. And you're now seeing more of the mergers and the interacting galaxies. And just so you can see that all on one page, this is 12 examples of just a random subset of data. Here's the top 12 when you just apply the machine learning alone. And here's where you've run the active learning. This is the top 12 objects that you haven't seen yet. So these are like the recommendations. Astronomaly thinks you'll like these galaxies. So to really test this out, we had to synthesize some data because by definition, we don't have a right answer for the real data sets because, you know, something can be anomalous, but is it interesting? And there's no real hard and fast rules for ways to label these. So we made some synthetic data in order to test the active learning part of our algorithm. And we made a very, very simple data set that was designed to be very easy for the algorithm to test it out. So what the data looks like is it kind of looks almost like transients. It almost looks like time series data, but it's not really. I've just drawn objects from various mathematical functions. So here there's two majority classes. There's sine waves, so I vary the parameters of the sine waves to make new types of objects, and this is a parabola. And what you're looking at on the left here is something called TSNE. It's a way of taking high-dimensional data and embedding it in a low-dimensional space to make it easy to visualize. So 99% of the data belong to one of these two classes, and you can see it makes these big clusters here. But what about all of this other stuff? Well, those belong to anomalies that I created. So the remaining 1% of the data belongs to one of three different classes of anomalies. So there's kind of this step function. This is a sum of sine waves, and there's a Gaussian. And now to kind of simulate the idea of some anomalies being more interesting than others, I pretended that it was the sum of sine waves that I was really interested in, and I hated the Gaussians. Those are artifacts. I'm not interested in them at all. And so we wanted to see how well the active learning worked in picking out the types of anomalies that I care about. And so one thing to note is that the interface is exactly the same. I just use a different plotting tool to work with this type of data. But you're once again seeing a random subset of my simulated data set. And you can see that most of them are the sine waves or the parabolas. However, if you run the anomaly detection algorithm, I think in this case it was LOF, and rank them from most to least anomalous, you can see it does a fantastic job of picking out the anomalies. So it's really prioritized them over the boring normal classes. But it's showing a lot of those Gaussians that I said I wasn't interested in, which is why I've been scoring them 0. In fact, in the top 10 or 20 or so, there weren't any of those sum of sine waves that I care about. So the idea being here is that you're dominated by some class of anomalies that you don't care about, like artifacts or something, and you might miss the ones that you really do care about. So you need to get rid of those artifacts as quickly as you can. And so after labeling just, I think it was about 100 in this case, and running the active learning algorithm, now in the top 10 or so, you can see there's a lot of those examples of the sum of sine waves and none of the Gaussians. So it's done a good job just getting rid of the things that I don't care about. So in terms of using this very practically, I can very quickly sift through a very large data set and get out the types of objects that actually interest me. Just to round off the simulation example with a visualization, so this plot is the same actually as this plot. So it's also a TSNE plot, it's just colored instead of with dots. And so it's showing you a region of what we call feature space, the different regions of feature space, and it's showing you how anomalous the algorithm thinks that region is. So with the raw machine learning, it finds this region very, very interesting. But I've provided these labels, and you can see that they cluster together. So the types of objects I'm really interested in are over here, and I'm not really interested in the ones over here. So once you run the active learning algorithm, you can see that the region that I'm interested in gets upweighted a lot. The region I'm not interested in gets downweighted. So anything new that comes in that's like over here, for instance, or near any of these zeros will get pushed way down the list. So I'm not likely to see it. And one final thing to point out is that if something pops up in a region of feature space that I haven't labeled, it just defaults to the raw anomaly score. So anything that's anomalous that I haven't labeled yet, I'm very likely to still see. So you're not going to miss anything this way. Okay, and now I'm going to finish off this talk with a few actual examples of using Astronomaly and other anomaly detection tools. So I promised showing you some MeerKAT data. Of course, I absolutely can't help it. So this is data from the MeerKAT Galaxy Cluster Legacy Survey, which was just recently published. And it's a publicly available, really beautiful data set. And what I'm showing you here are random subsets of the data centered on some sources. And you can see that most of them are pretty boring point sources. So you should just be looking at the thing in the center. And if I run exactly the same algorithm as I did for the optical data, you can see it does a pretty good job of picking out more interesting extended sources. So these tend to be radio galaxies that have a big supermassive black hole in the center, which is interacting with the gas and the dust in the region, producing synchrotron emission that spews out in these huge, beautiful jets, and then interacts with the intergalactic medium. So you get all these weird, interesting, twisty shapes that we're only actually just starting to study and understand. So the machine learning actually worked so well in this case, I didn't even need to apply any active learning here. But this is just a nice preview of some of the incredible objects that we've detected. Similarly, I've got a student who's actually now just starting his PhD with me, working in DECALS. So DECALS is a beautiful survey done with DECAM, a large chunk of the southern sky. And so he's been trying to run Astronomaly on this data set. Again, the thing that was really the most difficult was not adapting the machine learning parts, but being able to work with the data. You know, the Galaxy Zoo data was so pristine and beautiful and processed, and the DECALS data, you know, we really went for almost the raw data. So it was dirty, and there were artifacts, and it was noisy, and it was much more difficult to get the algorithms to work right. But as you can see from this top set of anomalous objects, it does a reasonably good job at picking out things that look interesting. I've also had another student who's just finished up with me on his MSc looking at transients. So he was looking at the Catalina real-time survey data, finding a few things like weirdly behaving carbon stars, flare stars, things like that. And this was a project done a couple of years ago now with Sarah Webb, who's now a postdoc in Australia. And she was also looking at transient data, and she had this big data set was completely unsupervised. There was no labels. We started off with 80,000 light curves, which is really quite a daunting task for someone to try to go through manually. And instead, we developed a fully unsupervised framework using clustering to try and find known objects like variable stars, and she made a few new discoveries of some variable stars that hadn't been seen before. And we also did anomaly detection, and that helped her detect this ultra-fast flare, which is quite interesting. And I really think more generally, this is quite a nice framework for how you can actually tackle these unsupervised learning problems when you have large data sets without any labels. And finally, the last two projects I want to talk about, the one is real-time anomaly detection. So when we were talking about doing anomaly detection in transient data, these are a set of light curves that we have stored on disk, and we want to do anomaly detection there, which you can use Astronomaly for already, no problem. But the problem is, if you find something weird, unless it's a variable star or something that's periodic, it's probably gone, and you'll never see it again. So what we really need to be able to do is to catch something anomalous when it's still, on the sky, when it's still changing in brightness, so that we can follow it up with other telescopes. And this is super important for Rubin. I mean, 10 million alerts a night, even if only 0.001% of those are interesting, that's still a lot of transients to follow up. So we have to be able to do anomaly detection in real time. And so this was work that I did with a student who's now a postdoc actually at MIT, Dan Krishna. And I had this very simple idea. I said that there are a lot of these types of objects that we know about, and we can model, right? We have predictions. We can make predictions for them. We have training data. So the idea is that we build a bunch of algorithms that are able to model and predict these light curves, and then anything that appears on the sky that doesn't fit any of our predictions could be an anomaly. And Dan had already a deep neural network designed to classify transients. So we thought, let's just adapt that to become a regressor, a predictor. And so the idea is that you see, this is simulated ZTF data. So you've got data points coming in, so the light curve is happening, so being observed. And the algorithm is trying to make predictions based on the points it's observed so far. And so you can see that the predictions are very uncertain initially, and they're kind of all over the place. But then as it gets more and more data, it gets more and more accurate. And this algorithm performs fantastically. Deep learning is an incredibly powerful tool, especially for these types of problems. So it was able to do pretty well with these predictions. The problem is, it actually did too well. So it was almost just learning correlations between points, such that even if we gave it a light curve that it had never been trained on, it was still able to do reasonably well at predicting the rest of the curve. So that's no good for anomaly detection, right? The whole premise is that it's supposed to do badly at predicting things it's never seen before. But so in this plot, you can see these are all blue because it's able to predict on the things that it's trained on, but these are also blue and they shouldn't be. They should be red. Only a few of the classes of objects that we gave it was it not able to predict. So instead, we went back to basics and came up with a more Bayesian approach, which was based on a model that we had for what we expected these light curves to sort of look like. A very simple parametric model, which we trained by setting the prior using training data. And it actually behaved a lot closer to what we wanted, in that the more anomalous classes couldn't really be super well fit by most of the trained models, so would probably flag up as anomalous. But I think our main conclusion from this was that this is a very difficult problem, and it's a really important problem to solve when Rubin starts taking data. Finally, the last thing I wanted to mention, which I'm really excited about, is also a deep learning approach called representation learning. So the reason I haven't really used too much deep learning up until now is it's mostly been driven by supervised learning. And I'm very much in the unsupervised regime. It's difficult to do anomaly detection, or to think of how to do anomaly detection, without having some way of representing your data. because generally you have to ask, is this object different from the other objects in the data set? To be able to ask that kind of question, you need to calculate distances, and that's very hard if you've got like an image with thousands of pixels and not, rotationally invariant, etc. So I haven't used deep learning terribly much until now, but there's a lot of excitement around things like self-supervised learning and representational learning, where you use trained neural networks as feature extractors for new data sets to solve other types of problems. And so this was really interesting work led by Mike Walmsley, who's a postdoc at Manchester. And so one of the things I'm learning the more senior I get is the trick is you find some very bright young person, you inspire them with some work that you did, and then they go on and they do it much better than you did in the first place. So Mike was able to, you can see here, the blue line is much higher than the green line. So he was able to very much beat the original Astronomaly paper for this particular data set, using a pre-trained neural network that was trained on a different data set for a different problem as a feature extractor, and then doing some machine learning with it. So it was a very interesting paper, and I'm really excited about this because especially when it comes to images, it's very difficult to get a good set of features that can really reliably extract the anomalies and figure out what objects are similar to each other. So representational learning, I think, is going to be it already is a very exciting field in machine learning. Okay, so I'm just about finished my talk, but before I give my conclusions, I want to take this opportunity to advertise something, which is the Supernova Foundation. So this is a mentoring program for women in physics that I'm the founder and director of. And I really want to encourage any women or people of gender minorities who are just interested in a program that's quite supportive, that offers mentoring. Please visit the website, think about applying either as a mentor or mentee. It's a really wonderful international program. We would really welcome you. All right, so to conclude, basically, machine learning is just an absolutely critical tool in facing this data deluge that we find ourselves suffering under, or enjoying, I should say, in astronomy. And we run the risk of missing really exciting discoveries if we don't find ways of automating anomaly detection. And so our attempt to answer this is Astronomaly. You're more than welcome to try out the code, and please just drop me an email if you get stuck. And please do check out the Supernova Foundation if you're interested. Thank you very much.
Michelle, thank you very much for the very interesting talk. We now have some time for questions. If you joined us on YouTube, you can ask your question. You can put your questions on the comment section. And if you joined us on Zoom, please raise your hand and ask your questions. So questions? Okay. While we wait, I have a question. In that research done with time series, where you applied Astronomaly.
Astronomaly, yeah, it's a mouthful.
Yeah. It was like you were extracting features, or thus we can try to find. I ask it because I work with time series, and determining periods, I don't think it would be possible. And I'm actually very interested in how to apply this kind of machine learning to time series.
Sure. So in this case, we did definitely extract features. So there's a feature extractor called FEATS, which has been used for many years in machine learning. But it's particularly for variable stars and things that are periodic. It does have a lot of features based on the Lochner spectrum, for instance. But it's basically like a kit of kind of standard useful features. Some of them are very simple, just the brightness in various bands, mean, standard deviation, that kind of thing. And some are a bit more complex, like the Lochner, etc. And so in the case of Sarah's data, where she was looking at the deeper, wider, faster survey, so she had this data set of light curves, which were on sort of minute timescale, so very, very short timescale. And a lot of the things in there are periodic, and so she found the features actually worked really well in this case. So she was able to use them to do this clustering. As you can see, there's a lot of structure in the feature space, so they were pretty effective there, and also for anomaly detection. But with this work that I did with my student, with Malema, even though it worked okay for the CRTS data, when we ran it on plastic, it really, where we have some actual anomalies, like these are known anomalies, it really didn't do very well. And I think it tended to just pick out the brightness as the most useful feature, which is, obviously not what you want from a feature extractor. So I think in general, especially when you're looking for kilonovae or weirdly behaving supernovae, things like that, things that are more transient in nature, I don't think the features are particularly good. So things that I'd like to try are the features that we use for classification of supernovae, for instance. So they're a wavelet-based feature extractor, which should be more sensitive to the actual shape of the light curve. Or even similar kinds of deep learning approaches, I think would work well here. But the hard part is the real-time anomaly detection. That's much more difficult than trying to detect anomalies from the entire light curve. And I think that's still very much a very active field of research.
Sure. Thanks, Anne. Another question, does noise plays a heavy role in the feature extraction?
Yeah, noise is always an issue. And this is why I think some careful thought needs to go into the algorithms. So things like BADAC, which I mentioned early on, which can take into account the uncertainty information, I think actually becomes more and more important when you get bigger and bigger data sets where you're going to start really struggling with the low signal to noise object. So yeah, very much, what Malema found with the plastic data is quite often the things that the algorithm would detect as being anomalous were just faint. So that's not really, it's definitely not what you want. And so that has to do a lot with the feature extractor as well. But I think incorporating that uncertainty information, I think will become important as we go forward. So yeah, very much, noise is very much a problem and something that we have to deal with.
Yeah, well, thanks. Thank you very much. There is a question from Rafael on the chat.
Actually, I have another question, Rodrigo, if possible.
Okay, go ahead.
Michelle, thanks a lot for the presentation. I'm actually very interested in astronomy, but I'm more of a machine learning guy. And that's a lot of interesting things. I'm sure to write you later about that. But one thing that I'm really curious is that, is there any interest or opportunities or general interest on explainable artificial intelligence for astronomy? Is there any sense of that? Okay.
Yes, yeah, that's a really good question. I think there's, as a field, I think there has been a lot of pushback from the skeptics about machine learning because of the lack of interpretability. We are very used to having our models that are based in physics, that have some explanation behind them, then we fit our parameters and we write a paper and it's great. So now machine learning comes along, which works so much better most of the time, but we don't understand it because it has these extremely large number of parameters, these very complicated models. So I think explainability, interpretability is very important, and I think there's a lot of interest in it in the field. Anomaly detection in astronomy is a little bit of a smaller field. It's still growing. It's a bit newer, but certainly in things like classification, and especially people are starting to use machine learning algorithms in very fundamental things like cosmology, where we have very high precision. We need to be able to trust our results, but now we're starting to bring in usually deep learning algorithms in actually doing things like parameter constraints, etc. And there's this general unhappiness if we don't understand these algorithms. So yeah, there's a lot of work in things like saliency maps, and I'm not super up to date on all the latest things people are working on, but I definitely think there's a strong interest from the community in being able to interpret these things, because more and more machine learning is becoming part of our pipelines. So we have these extremely complex pipelines that go from the photons hitting the telescope all the way to the end, where we might make some cosmological constraints or things like that. There's a very, very complex pipeline with lots of steps. And so we're bringing in machine learning more and more, but we have to be able to understand it. We have to be able to get uncertainties out of it. We have to know that it's unbiased, things like that. So I think there is a very, especially in cosmology, which is more my background, there's a strong demand for algorithms, often a stronger demand for algorithms being interpretable and understandable than you might traditionally find in industry. Although these days everybody's very keen on interpretability, I think.
Okay, thank you.
Sure.
Thanks, Rafael. More questions? Okay, people are thanking you, Michelle from YouTube, for the excellent talk.
And, I feel famous.
Okay, well, if we do not have more questions, I'd like to first thank Michelle for taking her time and giving us this amazing talk. Also reminding, please visit Michelle's project website, supernovafoundation.org. And
Great.
Well, this presentation will be available on our website and on LINEA's YouTube channel. And thanks again to Michelle. Thank you, Michelle.
Thank you. And yeah, if anyone's interested in chatting more, please feel free to email me. I'd be happy to start some collaboration.
Yeah, thanks. Okay, so everyone, have a great day. Stay safe, and I hope to see you all again on our next webinar. Thank you.
Thanks, everyone.